Hello everyone, this is Hossein from EJ Academy. This is another video in the series about quadratic expression. In this video, we wanted to talk about the constant of quadratic expressions. In the previous videos, we introduced the standard form of quadratic expressions. You see it on the screen. In this expression, x is the variable of the expression and a, b, and c are the constant. And in this video, we wanted to focus on the effect of these constant on the behavior or the shape of the quadratic expressions. In the previous videos, we also introduced another form of quadratic expression, which was the vertex form. And there are relationships between the constants of the standard form and the constants of the vertex form. And we obtained those relationships for you in the previous videos. I have left the links to these videos in the description below. If you're not familiar with the concept, now it's a good time to go ahead and check those videos. One of the advantages of the vertex form is that the coordinates of the vertex of the parabola is already available from the vertex form. If the coordinates of the vertex are x sub v and y sub v, x sub v is equal to h and y sub v is equal to k. As I mentioned earlier, the purpose of this video is to explore the effect of the constant a, b, and c on the shape of the parabola. I'm going to start with a, and let's head over to Desmos to see a couple of examples. The first example is y is equal to x squared. In this expression, a is 1, b and c are 0, and as you see, the shape of the parabola is upward. For our second example, let's change a from 1 to negative 1. So we have y is equal to negative x squared. Let me change the color to red. So as you can see, the second parabola is the mirror of the first one. And because a is negative, the parabola is downward. We can say that if a is positive, the parabola is upward. And if a is negative, the parabola is downward. Let's take a look at another example. This example is y equals x squared minus 2x plus 1. So in this example, a is 1, b is negative 2, and c is 1. And you see that the parabola is upward, and you can guess that the reason is because a is positive, similar to the first example. Our last example is similar to the previous one, but we change a from 1 to negative 1. So y equals negative x squared minus 2x plus 1. Let me change the color to orange. So the last parabola is downward, and you can guess the reason is because a is negative. Now that you saw some examples and got some ideas about the effect of the constant a on the shape of the parabola, it's actually time to prove when a is positive, the shape of the parabola would be upward, and when a is negative, the shape would be downward. As a reminder, I have written the standard form and the vertex form here for you. And here in this graph, we have an upward parabola, and we wanted to prove that if the parabola is upward, a has to be positive. So this point on the graph is the vertex, and the coordinates of the vertex is h and k. And this line here, this horizontal line here, is the line where y is equal to k. And this shaded area above this line is where y is greater than k. So in this shaded area, y is greater than k. Our parabola is located in the shaded area where y is greater than k. And if I substitute y for the vertex form, I would have a times x minus h squared plus k greater than k. And if I subtract k from both sides, I would have a times x minus h squared greater than 0. On the left hand side we have an expression that has to be positive, but the squared term is always positive, and as a result the multiplier a has to be positive. And this proves that if we have an upward parabola, a has to be positive. Now let's take a look at the other case. Now we wanted to prove that if the parabola is downward, a has to be negative. We're going to use the same method as we used above. This point here is the vertex of the parabola and its coordinate is h and k. This horizontal line passes through the vertex, has the equation of y equals k. And this shaded area below this line is where y is less than k. So this parabola is located in the shaded area where y is less than k. Now we substitute y for the vertex form, which is a times x minus h squared plus k less than k. Let's subtract k from both sides. If we do so, we have a times x minus h squared less than 0. On the left hand side, the squared term is always positive. So to have the left hand side to be less than 0, a has to be negative. And this proves that if the parabola is downward, a is negative. Now let's see how the location of the vertex changes as a varies. Here we have the standard form as well as the vertex form of the parabola, and also you see the graph of a hypothetical parabola. In the standard form, a is a variable, b and c are constant. Our goal here is to find an equation that gives us the location of the vertex as a varies. We are going to start by using the relationship between h and k in the vertex form and a, b, and c in the standard form. We know x sub v is equal to h, which is equal to negative b divided by 2a. We can multiply both sides by a divided by x sub v. On the left hand side, x sub v in the denominator will cancel out with the x sub v inside the parentheses, and on the right hand side, a in the denominator inside the parentheses will cancel out with the a in the numerator. On the left hand side we have a is equal to, on the right hand side we have negative b in the numerator, in the denominator we have 2 times x sub v. Now we use the relationship between k and a, b, and c. So we have y sub v is equal to k, which is equal to c minus b squared divided by 4 times a. Keep that in mind. In this equation, c is constant, b is also a constant, and a is a variable. We have already obtained a in terms of b and x sub v in the equation above, and we use that, we substitute that in this equation. So we get c minus b squared, and in the denominator we have 4 times negative b divided by 2x sub v. Now we rewrite this equation in this way. We have c minus b squared divided by 4 multiplied by the reciprocal of the fraction in the denominator, which is negative 2 times x sub v divided by b. The 4 in the denominator will cancel out with the 2 in the numerator. So we have 2 here. And the b squared in the numerator will cancel out with the b in the denominator. We have b in the numerator as well. Next line we have y sub v is equal to c -1 times -1 is +1. So we have plus b divided by 2 times x sub v. So the equation that we obtained here is a linear equation. This linear equation gives us the position of the vertex as a varies. Let's take a look at an example in Desmos to see if this equation actually works. Our example is y is equal to ax squared minus 2x plus 1. And the reason that I wrote a as a parameter is that because a here is a variable and we wanted to basically explore the effect of changing a in the shape of the parabola. So a is a variable, and as you can see, b is -2 and c is equal to. Let's add this equation into Desmos. Y is equal to a times x squared minus 2x plus 1. And Desmos gives us an option to add a slider for the variable a. So let's go ahead and do that. You see the effect of a in the direction of the parabola. When a is positive, the parabola is upward. When it goes to negative, the parabola becomes downward. Now let's use the equation that we obtained that gives us the position of the vertex. The equation is written here is y sub v is equal to c plus b divided by 2 times x sub v. Let's plug the values of b and c in this equation. So y sub v is equal to c, which is 1, plus b is -2 divided by 2 times x sub v. If we simplify this, we would get y sub v is equal to 1 minus x sub v. This is a line that the position of the vertex changes along this line as a varies. Let's add this line to our graph. Y is equal to 1 minus x. Let me reduce the speed so we can track the position of the vertex. Pay attention to the point that's showing the vertex and try to track it. As you can see, the vertex moves along this blue line as a varies between the negative and the positive values. To explore the effect of the constant b on the shape of the parabola, I'm going to use an example here in Desmos. The example is y is equal to x squared plus b times x plus 1. And I have an option to add a slider for b, consider b as a variable. Let's go ahead and do that. The reason is because I wanted to change b to see how changing b will affect the shape of the parabola. I'm going to reduce the speed to half. I'm going to change the range from -5 to 5. So let's go ahead and start the animation. If you remember when we were exploring the effect of the constant a on the location of the vertex, we found out that the location of the vertex moves along a line, but here we don't see that kind of behavior and the position of the vertex doesn't move along a line when b changes. Besides, you see here changing the constant b doesn't change the direction of the parabola, and basically the parabola stays upward, and that's because the constant a is +1, and because of that the direction of the parabola is upward. Now I'm going to use the relationship between the standard form and the vertex form to calculate the location of the vertex as b varies. Let's get back to our notes. So the goal here is to find the location of the vertex as b varies. Here in the standard form, a is constant, also c is constant, and b is a variable. We already know the relationship between x and y coordinates of the vertex and the constant h and k in the vertex form. So based on that relationship, we have x sub v is equal to h, which is equal to negative b divided by 2a. And as a reminder, b is a variable here and a is a constant. So I'm going to use this relationship to find the variable b in terms of the other two variables x sub v and a. To do so, I'm going to multiply x sub v by negative 2a, and also on the right hand side I'm going to multiply negative b divided by 2a by negative 2a. So I can simplify the right hand side, so negative 2a will cancel out with the negative 2a on the denominator, and I would have negative 2a times x sub v is equal to b. The second equation that I'm going to use is the relationship between y sub v and the constant k, which is y sub v is equal to k, which is equal to c minus b squared divided by 4a. In this equation, again, a is a constant, c also is a constant, and b is a variable, and I have already calculated b in terms of a and x sub v. So let's go ahead and substitute that value into this equation. I have c minus, instead of b we have negative 2a x sub v, the whole expression to the second, divided by 4a. Let's take one more step to simplify this further. We have c minus 4a squared x sub v squared divided by 4a. So 4a squared in the numerator will cancel out with the 4a in the denominator, and we are left with a in the numerator. So if I rewrite this expression, I would have y sub b is equal to c minus a times x sub v squared. This is the quadratic expression that gives us the location of the vertex of the parabola as b changes. So this is the location of the vertex as b varies. The example that we have in Desmos is y is equal to x squared plus bx plus 1. In this example, a is equal to 1, b is a variable, and c is equal to 1. And if we substitute these values into the expression that we obtained for the position of the vertex, we will get y sub v is equal to 1 minus x sub v squared. Let's get back to Desmos and add this quadratic expression to the graph and see if the vertex actually moves along this parabola. The new parabola is y is equal to 1 minus x squared. Let me change this to a dotted line. As you can see, the vertex of the original parabola moves along the dotted curve that we calculated here. So we can conclude that the effect of the constant b on the shape of the parabola is changing the position of the vertex of the parabola. Unlike the constant a, changing the constant p doesn't change the direction of the parabola, it only changes the location of the vertex of the parabola. Finally, it's time to see the effect of the constant c on the shape of the parabola. The best way to demonstrate it is to see an example, and the example I have here is y is equal to x squared plus c. And if I animate c, you would see that changing c causes the vertex of the parabola to move up and down. Let's take a look at the vertex form of quadratic expression to see what's happening here. This is the vertex form, and here we have the relationship between the coordinates of the vertex and the constant h and k in the vertex form. Because here we're focusing on the effect of changing c on the shape of the parabola, a and b are constant and c is a variable. As you can see, changing c doesn't change the x coordinate of the vertex, it only changes the y coordinate of the vertex in a linear fashion, and as a result the vertex only moves up and down. Now let's recap what we covered in this video. We knew that the quadratic expression has three constants a, b, and c, and we explored the effect of each constant on the shape of the parabola or the curve resulting from the quadratic expression. Regarding the constant a, changing the constant a changes the direction of the parabola from upward to downward. Basically, for positive a's, the direction of the parabola is upward, and for the negative a's, the direction of the parabola is downward. Also, changing the constant a changes the location of the vertex of the parabola. Basically, it moves the location of the vertex along a line, and we obtain the equation of that line. Changing the constant b didn't change the direction of the parabola, but it caused the vertex of the parabola to move along another parabola, and we use the vertex form of the quadratic expression to obtain the equation of that parabola. And finally, changing the constant c only caused the location of the vertex of the parabola to move up and down. That was it for this video. If you have any questions regarding the quadratic expressions in general or the effect of the constant on the shape of the parabola, let me know in the comment section below this video. If this video helped you in any way, please hit the like button and subscribe if you enjoy our content and would like to see more.